We are now at the last stretch of our discussion on interactions of ionizing radiation with matter. This time, we'll talk about what happens to neutrons as they pass through matter. As we know it, neutrons have no charge, so they do not interact with the electrons like alpha and beta particles do. Neutrons interact mainly with the nucleus of our atom. And just like gamma rays, neutrons are highly penetrating, especially at high energies, and their biological effects are strongly dependent on these energies. Arbitrarily, we can classify neutrons according to their velocity or their energies. So we can divide them into either slow neutrons, or we have a special name for the slow neutrons. We call them thermal neutrons. Or we can also classify them as fast neutrons, especially if they have energies that are above or equal to 1 mega electron volt. Since a neutron has no charge and can easily enter into a nucleus, they can also easily cause a reaction in the nucleus of our atom. Because of this, it is best to start our discussion of neutron interaction with a review of nuclear reactions. You've learned about spontaneous nuclear reaction in lecture number 1. This reaction happens naturally due to the innate instability of the nucleus of a radioactive atom. There is another nuclear reaction that is often referred to as induced transmutation that occurs when an elementary particle, such as a neutron, bombards with the nucleus of an atom. And this neutron can have, or this elementary particle have enough energy to disturb the internal structure of the bombarded nucleus. A nuclear reaction can be described by identifying the incident particle, the target nucleus, and the reaction products. And we can write them using two typical notations. One, the longhand notation, as we normally refer to, because we are individually writing down our projectile, our target, and then our product and our ejectile, or the shorthand notation here, which generally tells us that the same elements, our target, our product, our projectile, and our ejectile, but in a much shorter fashion. So our projectile can be any nuclear particle, and this could be also another nucleus of an atom, which will collide with the target to initiate the nuclear reaction. Our target X here, or our target nuclei, is usually at rest, and this heavier nuclei compared to our product nuclei here, Y. In this sample nuclear reaction, for instance, where we have a neutron striking a nitrogen nucleus, producing a proton and an isotope of carbon, can be written as this nuclear equation right here. Or, in shorthand notation, this can be written as our target nucleus nitrogen being bombarded with a neutron, producing carbon and proton. Additionally, this nuclear reaction can also be described generally as simply a neutron-proton reaction. So here are other examples of nuclear reactions involving a variety of projectiles and ejectiles. The D here refers to deuterium. So this reaction right here can be classified as deuterium neutron reaction. Other reactions that are notable, we have here gamma and neutron reaction, or neutron and gamma reaction, where we have a neutron bombarding a target nucleus and producing a gamma ray as one of its products. Many new radionuclides have been produced by bombarding nuclides of naturally occurring elements with neutrons, protons, deuteriums, or alpha particles. All nuclear reactions obey certain conservation conditions, which includes the conservation of nucleons, the conservation of charge, the conservation of energy, and the conservation of momentum. As defined, the conservation of energy tells us that the total energy before and after the reaction is the same. So that means that the sum of the energies, kinetic energy and rest mass energy of our reactants right here should be equal to the total energy of our products right here, which is the sum of the kinetic energies of our ejectile and our product Y, including their rest mass energy. Now, there's an important information that we can derive from inspecting the energies involved before and after the nuclear reaction. In fact, the rest mass energy before and after the reaction are not the same at all. And if we get the difference between the sum of the rest mass energies before and after the reaction, we will get a value which we call as Q value. So if we will just rearrange this, combine rest mass of our reactant and our product, and then simplify, we'll get the Q value equation, which is equivalent to simply mc squared. A positive Q value is indicative of a release of energy in the reaction. And so we call this reaction as exothermic. On the contrary, a reaction with a negative Q value will be endothermic, and hence it cannot take place unless the incident particle is accelerated to have a minimum energy Q. This indicates also that the incoming particle should have a minimum threshold energy for the reaction to take place. Nuclear reactions that are induced by the interaction of neutrons with matter can be exothermic or endothermic. Here are the mechanisms of interactions of neutrons with matter. When neutrons pass through matter and interact with the nucleus of the atom, the neutron is either scattered elastically or inelastically, or the neutron is absorbed by the nucleus, which results to some interesting nuclear reactions like radiative capture, charge particle reactions, the production of neutrons, and fission or spallation. Let's take a look at each of these interactions, when and how they happen. Neutron scattering occurs when a nucleus, after having been struck by a neutron, emits a single neutron after the collision. This initial neutron right here and this final neutron right here do not have to be the same, which means that this neutron can knock out a neutron from the nucleus of this atom, or just like a billiard ball, it can also just simply be elastically scattered through here as the nucleus recoils. So the recoiling of our nuclei here causes our nucleus to lose its energy via excitation and ionization. In inelastic scattering, where a neutron interacts with a large nucleus and gets scattered like a ping pong ball striking a bowling ball, some energy from the incident neutron is transferred to the nucleus. The scattered neutron, right here, now moves slower than the incident neutron. The nucleus is in an excited state, and as it recoils, it releases gamma rays. In radiative capture, the incident neutron gets absorbed by the target nucleus and as a result forms a new isotope that's a next higher isotope of the original target right here. This new isotope is in an excited state and de-excites by emitting gamma rays. Hence, we can write a general description of radiative capture as simply a neutron gamma reaction. Charge particle interactions works the same way as radiative capture. The only difference is that after our neutron is absorbed by the target nucleus and after forming a next higher isotope of this original nucleus right here, this excited isotope de-excites by emitting charged particles instead of gamma rays. So these charged particles can either be a proton, an alpha particle, sometimes a beta particle, and other fragments. In nuclear fission, the incoming neutron is also absorbed by the target nuclei, but instead of just releasing either a gamma ray or a charged particle, this excited nucleus splits into two nuclei. We call this as fission fragments, and also releases more neutrons in the process. Perhaps a more interesting question to ask is how frequent do each of these interactions occur whenever a neutron passes through matter? To determine this frequency, it is necessary for us to describe first the availability of the neutrons that would cause this interaction and the probability of a neutron to interact with the material. The probabilities exist for any of these interactions to occur, depending on the energy of our incident neutron and the type of nuclide with which the neutron interacts. The availability of neutrons that can cause this interaction is described as the neutron flux going through that matter, and the probability of interaction with the neutron and the material is called the nuclear cross-section. We can also think of this probability of interaction as a measure of the capturing power of a particular material for neutrons of a particular energy, causing an interaction. The nuclear cross-section, or simply the cross-section denoted by the symbol sigma, is the probability of a particular reaction to occur between a neutron and a nucleus. In other words, this is the effective area that the nucleus presents to the neutron for a particular reaction to occur. The larger the effective area, the greater will be the probability for this reaction. Cross-sections can either be microscopic or macroscopic, and it is dependent on three things: the type of reaction involved, the kind of nucleus involved, and the energy of the neutron. For instance, the absorption of a thermal neutron or a slow neutron in most materials is much more probable than the absorption of a fast neutron. The cross-section is defined in units of barns, which is equivalent to an area of about 10 to the negative 24 square centimeters on the basis of the radius of our atomic nuclei being about 10 to the negative 12 centimeters. There are reference sources of nuclear data that provides the neutron cross-sections for various nuclides and neutron energies. So thankfully, we don't have to calculate this cross-section anymore. Let's take a look at some examples. Here is a plot of the total cross-sections of hydrogen and boron at various neutron energies. We can see from the graphs that the cross-section, right here on the y-axis, it decreases as the energy or velocity of our neutron increases. That means that the neutron reactions with the nuclei of hydrogen and boron in this example obey a general rule of having some proportionality to the inverse of the energy or the inverse of the velocity. This inverse proportionality of cross-section and neutron velocity is particularly pronounced in certain regions of energy, as illustrated here in these curves. So, for instance, in hydrogen, it's more pronounced on this area, and then it plateaus here along this energy range, and then follows the same relationship again. In boron, that would be in the range of 0.01 to around 100 or so electron volts. And we expect other materials to also show the same relationship. But this is always not the case though, as there are nuclides at certain neutron energies where there exists a resonance between the neutron energy and the nucleus of the target atom. At some neutron energy ranges, certain nuclei have a high capacity for interaction with neutrons. And these elevated neutron cross-sections at some specific neutron energies appear as sharp peaks in plots of cross-section versus energy of that nuclei, such as this one. This is a plot of the cross-section of manganese. So these peaks right here that we see are called resonances. And these are often associated with a neutron gamma reaction. They occur when the energy of the incident neutron corresponds exactly to the quantum state of the excited compound nucleus, which is already the newly formed nucleus consisting of a compound between the incident neutron and the target nucleus. Most nuclides display both the inverse relationship of energy or velocity on cross-section, just like this one here, and the resonance effects over the entire possible neutron energy spectrum, such as this plot here. A typical plot, therefore, of neutron absorption cross-section with energy can have 2 or 3 distinct regions that looks like this. So we have the region wherein there is a high absorption cross-section and the inverse relation of velocity and cross-section exists. We have the resonance region, and further along the line, we have the fast neutron region where there is a steady decrease of cross-section as the energy increases. As you might have noticed in the examples that we have presented, we use the term total cross-section instead of just cross-section. That is because each nuclear reaction is denoted by a characteristic cross-section. Keep in mind that neutron cross-sections, or simply cross-sections, can be specific and differ in value for certain reactions. For instance, the elastic scattering cross-section might be different to the inelastic scattering cross-section, or the fission cross-section, or the capture cross-section of that particular nuclei. Hence, we can get the total cross-section by simply adding all of these possible cross-sections of the neutron and the nuclei. The total cross-section measures the probability that an interaction of any type will occur when the neutron strikes the target. Let's take a look at an example. The thermal neutron cross-section for uranium-235 at 0.0253 electron volt, or at a velocity of 2,200 meters per second at room temperature, is found to be 0.001 barns for alpha particle producing reactions, 95 barns for neutron capture reaction, and 586 barns for fission reaction. Summing up this cross-section, we get a total of 681 barns. So the total cross-section of a uranium-235 atom is 681 barns. What other information can we get here? So as we have mentioned before, cross-sections are probabilities of interaction. So what is the likelihood, for instance, of a neutron capture reaction to occur when a uranium-235 atom is bombarded with a neutron of energy 0.0253 electron volts. So using our total cross-section and our given cross-section for neutron capture reaction, we can get this probability by simply getting the ratio of our neutron capture neutron capture cross-section and our total cross-section. So we have 95 divided by 681 barns, multiply that to 100, we'll get 14%. So this means that the probability of neutron capture reaction to occur when uranium-235 is bombarded with neutron of energy 0.025 electron volts would be 14%. For fission, that would be much higher because our cross-section here is about 586 barns. And so computing for the probability, that would be around 86%. And indeed, experiments verified that these probabilities are true. So in summary, neutrons can have many different types of interaction. This can be either scattering or absorption. And under scattering, we have elastic and inelastic scattering. And under absorption, we have various other nuclear reactions. Now, because neutrons interact with our nuclei in various ways, each of these interactions has their cross-section. Summing up, the total cross-section will give us the sum of all possible reactions. And we can visualize the probabilities of these reactions using this pie right here. So we see that there is more probability for scattering to occur compared to absorption. But of course, that would depend on the energy of our incoming neutron as well as the material in which the neutron passes through.